Good afternoon, everyone, and welcome to yet another lecture on energy management and energy conservation in thermal systems. We have up till now discussed with the boiler system. We have also discussed with the steam system, and today we are going to discuss the furnace. So, general fuel economy measures in boilers we have covered. Also, we have talked about the steam and steam leakages, also steam trap. Today we will discuss about furnaces and waste heat recovery. A furnace is an equipment to melt metals for casting or heat materials for change of shape, that is rolling, forging, or change of properties like heat treatment. So you must have come across various furnaces. Like we have done one experiment on in material technology lab in which we do end quenching. So to prepare the specimen for end quenching, we put it in furnace. This is an electric furnace, and so there are different classification of furnaces are classified on the basis of heat transfer, mode of heat transfer, into open hearth furnace and through a medium, heated through a medium furnace. So open fireplace furnace or open hearth furnace are the furnaces in which the material is kept, or the furnaces are open and in which the material is being placed. So according to mode of charging, it can be a batch process. That means some specified quantity is being placed inside the furnace, or it can be a continuous process. Like for example, if we take an example of manufacturing of glass, so in that the process is a continuous process. So in batch process we have the re-rolling or continuous pusher or forging operation, in which batch of material is being placed in the furnace, it is taken out and another process is being carried out on that specimen. Or it can be a pot type of equipment in which setup in which the batch of the material can be processed. Okay, so according to mode of heat recovery, so based on so heat recovery devices are there for furnace. It can be recuperative or regenerative. Recuperative means the transfer of heat takes place with the same it is separated by a medium, whereas regenerative is the two mediums will get in contact with each other. Okay, how to see that the furnace is efficient? That means there are some characteristics by which we can say that the furnace is efficient or not. So there are some five properties by which we can say the furnace is effective. Furnace should be designed so that it is that in a given time as much of material as possible can be heated. That means you put a material inside the furnace, it should get heated with a minimum possible time. Okay, with a uniform temperature. It should not be that the temperature must be uneven. That at some place we are having higher temperature, whereas at other place we have lower temperature. So that can hamper the property of the material. Okay, so you must have seen blacksmith. You put the material in the furnace, heat it up, and then the other operation is being carried out on that equipment or that specimen. Okay, so you must have seen that there is an episode on History Channel about forging. So I would insist that you see that episode, and in which the important all processes are important, right from heating to quenching. Okay, and with the forging also, right. To achieve this, the following parameters are considered, that is the determination of the quantity of heat to be imparted to material or charge, liberation of sufficient heat within the furnace to heat the stock and overcome all heat losses, transfer of available part of that heat from the furnace gases to the surfaces of the heating stock, equalization of the temperature within the stock, reduction of heat loss from the furnace to the minimum possible extent. Okay, so you see, these all are the parameters by which you can make the furnace efficient. What are the various types of furnaces that is being shown over here? So based based on these parameters, furnace energy supply, what type of energy is supplied to the furnace? It is in the form of liquid fuel, gaseous fuel, or it is in the form of electricity. So why we are saying this? Because some materials will not tolerate sulfur sulfur in the fuel. So those kind of fuel will not be used in the furnace. Whereas solid fuels, if we are using like coal, so particulate matter will be a problem. Okay, so selection of a proper energy supply is very important. Then there are oil fired furnaces, mostly used as light diesel oil, LDO we say, where presence of sulfur is undesirable. Okay, so furnace operate with very low efficiency as 7% or up to 90%. So there are furnaces available who are having efficiency of 7%, and also there are up to 90%. Okay, so regarding temperature can be from the range of 100 degrees Celsius to 1300 degrees Celsius to 3500 degrees Celsius. So where wide ranges of furnaces are available, you have to select what particular temperature is required for your material. Okay, so this typically, the first figure which is shown over here is a forging furnace. So forging furnace are used for preheating the billets to attain a forge temperature. Normally the temperature is around 1200 to 1250 degrees Celsius, and typically there is a operating cycle can be divided into heat up time, soaking time, and forging time. So what happens is the billets which are there, which are shown over here in the figure, are placed inside the furnace for some time, which is called as a heat up time. Then the material is being soaked or kept in that furnace for some time, which is called as a soaking time, and then it is removed and then it is forged. So normally 4 to 5 hours inside the furnace is considered to be to attain a uniform temperature depending upon the size of cross section of the material. Okay. Then there is a re-rolling type of mill furnaces, continuous pusher type or batch type, or continuous steel reheating furnaces. Okay, so you see that a typical furnace we have will have this type of heat transfer. That means it will have a flame, and complete furnace design should be such that the radiation effect is, or it will have a refractory substance inside the furnace, so that the heat will be transferred by radiation, it will be reflected by the internal material, and the stock is kept in such a way that the heat will be supplied to this stock through convection. So radiation and convection is the only mode of transfer of heat taking place inside the furnace, whereas conduction will be kept to minimum, because conduction is only for the heat loss through the walls of the furnace. The next figure which is shown over here is a cupola furnace. So cupola furnace is familiar to you. It is a tall cylindrical melting device used in foundries to melt iron, pig iron, cast iron in foundry. So what happens usually is it is a material is being placed, alternate materials of coke and metal is placed on top of each other, and this is called as a flux. So flux may be limestone or fluorspar or sodium carbonate or calcium carbonate. So limestone is also involved. Limestone is major part of the flux, approximately one fifth of the weight of the coke charge. And so what happens is when the heating, it is heated by some uh, heating devices from the bottom, or either the wind is blown over here. So what happens is, because the metal gets melted, and it will reside at the lower portion of the furnace, thereby the coke will be floated on top of it because it is a lightweight than metal. And so what happens is it be uh, as the combustion takes place, the material, the charged material, that is the coke, flux and metal, will be descending downwards, while the hot gases due to combustion will be ascending upwards. So heat exchange takes place between the rising hot gases and the descending charge, thereby melting the metal. So the liquid metal drops down while the coke floats on top of it. So the flux also melts and reacts with impurities of the molten metal, forming a slag. So you see there is a slag layer is there. This slag floats on the surface of the molten metal, and it prevents the oxidation of the metal. Okay, so there are different zones of the cupola furnace, which is well zone, zone. So all reactions taking place in the combustion zone is the oxidation of manganese and silicon, which evolves the heat. Whereas in the melting zone, iron gets converted into iron carbide. Okay, then hot blast cupola is there, in which the temperature can be as high as 800 degrees Celsius, where sensible heat is added and it activates the combustion of coke, leading to rising combustion temperature. Then there are induction furnaces, there is a walking beam furnaces, right? So different types of furnaces are there, which are we are operating for different applications. Okay, so moving further, so you see that there are some general guidelines or fuel economy measures in furnaces. We will discuss one by one. Okay, so uh, here you see that in the complete combustion with minimum excess air, it is seen if we plot the exhaust gas loss versus the air ratio. You see as the exhaust gas temperature increases, the air ratio required is lesser. So if you maintain a minimum excess air content, then your exhaust gas loss percentage will come down to 40%. Whereas if it is 1000 degrees Celsius exhaust gas temperature, and if you maintain the air fuel ratio at around 1, then the exhaust gas loss will be around 70%. That is not desired. Okay, so all these methods. So if we talk about performance evaluation of the furnaces, there are two methods, same as boilers: indirect method and direct method. Direct method efficiency calculation is directly heat required by the stock divided by the heat evolved by the fuel consumed, okay, for heating the stock. So this way we can calculate the thermal efficiency of the furnace. Indirect method, we can calculate the percentage of carbon dioxide, carbon monoxide, percentage excess air, and everything taken together, and heat balance is done, and then convert calculated the efficiency of the furnace, same as that of the boiler. So we are not covering it. So second economy measures in furnaces is the proper heat distribution. You see that the stock and flame should not come in contact with each other directly. Okay, there should be some space so that the proper mixing of the flame takes place. Because I have shown you that the heat transfer by the flame to the stock should be by method of convection and radiation. Okay, so proper flame propagation. This is the wrong method of flame propagation. There should be two flames involving so that the entire flame furnace area is being covered. So major losses which are taking place from the furnace are the heat loss from the wall and heat loss by the opening of the furnace, because when we put the stock through the opening, there will be losses through that opening. Okay, so one must think of overcoming these losses from the furnaces. Also, air infiltration is there. So air infiltration from cracks or doors or wind or the openings of the furnace. Then radiation heat loss from the opening, cooling media heat loss, which is the medium which is being used as a cooling water or air, so that after adequate flow of cooling media is essential, because it might possible that the furnace may not be insulated from the outside. Okay, so material handling losses, that means if the material is to be carried to another process and it is the distance is large, so we have to increase the temperature of the billet so that when it reaches the other process, it should not reduce its lose its heat. Otherwise, the material structure will change. Okay. Then third one is the maintaining optimum operating temperature of the furnace. So it is seen that the operating temperature has direct effect on the efficiency of the furnace, because you see that operating at too high temperatures than optimum causes heat loss or excessive oxidation or decarbonization or overstressing of the refractories. So there should be complete judgment of what temperature is required for a particular uh, material. Like slab reheating furnaces will require a temperature of 1200. Rolling mill furnaces will be requiring a temperature of 1200. Bar furnace for sheet metal, sheet mill will have temperature lesser. So you have to have entire knowledge of what should be the required temperature in the furnaces. You should not go over that temperature. Then prevention of heat loss through openings, right? So heat loss through opening consists of heat loss by direct radiation through openings and the heat loss caused by combustion gas through leaks through openings. So there is a formula, there is an empirical formula given to calculate the heat loss from the opening, which is by radiation. So radiation you have sigma A and T raised to 4. Okay, so T is the absolute temperature into area, then refractive index of the refractories. All these things will come into consideration. The time of operation, everything multiplied together will give you the total heat loss through openings. How much time the opening was, the inlet or outlet of the furnace was open for inlet of material and outlet of collection of the finished heated product. Okay, if the furnace pressure is slightly higher than outside air pressure, then what happens? The basically what happens is the furnace inside pressure is kept higher than the surrounding to minimize the infiltration rate. If the inner furnace inside temperature pressure is lower, then infiltration will take place. Okay, so fifth point will be control of furnace draft. What is the meaning of this? Same thing. If the negative pressure exists in the furnace, air filtration is liable to occur through the cracks and openings, thereby affecting the air fuel ratio control. Okay, it is seen that for slight that means if the furnaces are airtight, still there is a 40% infiltration rate inside the furnace. Okay, so infiltration is to be avoided, whereas exfiltration is not so serious as compared to infiltration. Why? Because exfiltration is nothing but leaping out of the flames or overheating of the furnace refractory, leading to reduced brick life. Okay, and maintenance will be increased. Right. So sixth point is optimum capacity utilization. It is similar to loading of the boiler. Right. If it is poorly loaded, that means you are providing the flame, but there is no material to heat, then that can cause inefficiency in the furnace. So you should have an optimum capacity of the furnace, or you should run your furnace at optimum capacity. Okay. Now, what is the best method of loading? The best method of loading is a trial noting. So trial noting of the weight of the material put in at each charge. So each batch you measure the weight which is being put on, or how much time it takes for the temperature, or how much amount of fuel is being used. So all these things taken into consideration, you will get the optimum value of the material to be loaded inside the furnace. Okay. Next one is waste heat recovery from furnace flue gases. Any industrial furnace, the product of combustion leaves the furnace at a temperature higher than the stock temperature. So stock temperature is required is 800 degrees Celsius. You will not maintain your furnace at 800, but you will maintain your furnace a slight higher temperature, which is say 900 or 1000. So we have said while discussing with the boiler that if the stack temperature is more than 200 degrees Celsius, it is a having a potential for waste heat recovery. Okay, so whenever the sensible heat of the flue gases recovered depends upon what will be the charge or preheating of the combustion air or utilization of waste heat for other processes. So we can preheat the charge with the help of these flue gases, similar to economizer in the boiler, that we preheat the water. feed water. Similar way, we can preheat the charge. So when raw materials are preheated by exhaust gases before being placed in the heating furnace, the amount of fuel necessary to heat them in the furnace is reduced. So raw materials are usually at room temperatures. They can be heated significantly using high temperature gas to reduce fuel consumption rate. Or we can use preheating of the combustion air. Similar to we have discussed about turbocharger in automobile. Similarly, we can use preheating of combustion air, okay, with the help of flue gases. So these all things will come under waste heat recovery from furnace flue gases. So there are radiation recuperators or convection recuperators available to preheat the feedstock. First one is 1 minute. Hello, am I audible now?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so we were discussing about the seventh point. Then we have the minimizing of wall losses. So you see that every furnace will have different types of refractories. This wall is called as a refractory. So about 30 to 40% of the fuel input to the furnace goes to make up for heat losses in intermittent or continuous furnaces. Take an example of the process of Parle-G biscuit when the dough is mixed. Okay, the dough is mixed and it is transferred to the furnace. So during this time, it should not lose its consistency. So for that, a preheating is required. Okay, or intermittent heating is required. So about 30 to 40% of the fuel input will go into heating of this. Okay, so the heat loss from the furnace wall affect the fuel economy considerably. The extent of wall losses depends on what will be the emissivity of the wall or thermal conductivity of refractories or wall thickness, whether the furnace is operated continuous or or intermittently. So all these parameters will take into consideration, and the brick lining or furnace wall is to be maintained, because whenever a person is operating near the furnace, They should not feel the heat coming out of the furnace. So furnace wall should be such a way that there should not be any heat leakage from inside to outside, right? So you know that you have undergone the formula for heat transfer, that heat transfer through conduction, and you can directly calculate what should be the rate of heat transfer from the furnace. So how to prevent, by the way, the radiation heat loss from the furnace? How to prevent the radiation heat loss? So there are refractory material available to by which you can minimize the heat loss from the furnace through radiation. Uh, example, use of ceramic fiber. So ceramic fiber is a low thermal mass refractory. Ceramic fiber is a low thermal mass refractory used in hot phase of the furnace and fastened to the refractory walls. Due to its low thermal mass, the storage losses are minimized. This results in faster heating up of the furnace and also faster cooling. So there are some ceramic fibers which are placed inside the furnace wall. Okay, it is kind of an insulation. So when we talk about insulation and refractories, it will be discussed in detail. So ninth point is use of ceramic coating. So ceramic coating in furnace chamber promote rapid and efficient transfer of heat, uniform heating, and extended life of refractories. So you must have seen that whenever red brick, take an example of red brick. You must have seen that red brick becomes gray if it is overheated. Okay, so it is a clay. So clay, if it is heated more, it becomes brittle. So it will not be used in construction purpose, right? So right amount of heating is required for a particular material. So ceramic coatings are high emissivity coatings, which when applied, we has a long life of temperature up to we can say it can handle up to 1500 degrees Celsius. So depending upon your application, you can select a type of coating which can be coated inside the refractory material, or it can be coated outside the furnace wall. Then you have to see that if the coatings are non-toxic, non-flammable, and water-based. So you see that energy saving of order of 8 to 10, 20% as reported. You can find literature which reports 8 to 20% of the energy saving when furnaces are operated at lower temperature with the help of refractory coatings and fiber. Okay, so this is all related to general fuel economy measures which are found in furnaces. If you look at the fishbone diagram of furnaces, you see that this figure depicts each and every component that we have discussed right now. So you see it is combustion control, recovery of waste heat, or it is related to equipments, and you see if the furnaces operations are there, and insulation. So all these things are represented by a fishbone diagram. Each and every point represents. So if you want to control your combustion, then this part is to be looked upon. If you want to control the equipment part of the furnace, then you see improvement of gas flow, then burner position, maintenance, all these things are to be noticed. If you want to go for operation, then how heat can be improved, what will be the rate of operation, what will be the feed rate of the stock, what can be the material arrangement, how to do the dropping discharge temperature. So all these things needs to be studied, and this overall one particular diagram gives all the summary of what we have discussed up till now related to furnaces. Okay, right. So take a 2 minute pause and think about what all things you require more to be understood in these furnaces, or whether it is going at a good pace. I would like to have a feedback from your side. So is it okay up till now? Everything is understood? Okay. Yeah, nice. So now this puts an end to the furnaces part. So the question will be what will be the questions based on these furnaces we will discuss at the end of the lecture. Okay. Right. Okay, then we come to insulation. So insulation is always accompanied with refractories. Mind well. Insulation should be always accompanied with refractories. Right. So insulation and refractories, but for our syllabus, we have only insulation part. So we will discuss that. And this already you have done in lower semesters in heat transfer. That what will be the critical thickness of insulation. Do you remember this critical thickness of insulation? For given material, steam is flowing inside the pipe, so you have the radial insulation of different materials. So lower conductivity insulation should be first, or higher conductivity insulation should be first, and so on. What should be the critical thickness of insulation? So I would like to recall what is critical thickness of insulation. Can anybody tell me critical thickness of insulation? You can unmute yourself and then answer. Anyone? What is critical thickness of insulation? If you don't know, say don't know in the chat section.
Minimum level of thickness which is required for insulation, means to achieve high effect.
Can you elaborate? So see, whenever there is a electrical wire is there, electric wire will carry current. So always it is seen that whenever the current is carried by a conductor, its temperature will increase. Okay. Now and we cannot keep the wire bare because electric shock may be experienced. So we should cover this. Now what happens when we cover it with insulation? Because insulation is a bad conductor of heat and electricity. So if you cover it with insulation, it is possible that the insulation will not allow the heat to dissipate to the surrounding. So critical thickness of insulation is that insulation at which the heat transfer rate is maximum. Okay. So, but for our purpose, this we have studied in 5th semester, that the insulation should be critical thickness of insulation so that heat transfer is maximum. But here we require that the insulator should be economic thickness of insulation. Now there is difference between critical thickness and economic thickness of insulation. So economic thickness of insulation we are going to discuss in this semester, whereas critical thickness we have discussed in the previous semester. Okay, so if you have any difficulty in critical thickness of insulation, you can put it in the chat section. In our WhatsApp group, we will discuss more there. So here we will talk about the economic thickness of insulation. Okay, so insulation, it is a poor conductor of heat and low thermal conductivity. Insulation is used in buildings and in the manufacturing process to prevent the heat loss and heat gain. Okay, so basic features of insulation is to reduce overall energy consumption, offer best process control by maintaining process temperature, prevents corrosion by keeping the exposed surface of refrigerated system above dew point, and provides fire protection to equipment. So it is not just related to furnace or boiler, but it is related to in general. So you see the ducting of the refrigeration and air conditioning setup are put up with some insulation, right? Boiler steam pipes are also put up with some insulations. Okay, and you see that there is a silver color paper which is being wrapped around the insulation material from the outside. So this is to minimize the radiation heat loss. Okay, so insulations can be classified into 3 types, which is the low temperature insulation, which can handle up to 90 degrees Celsius, medium temperature insulation, which is 90 to 325 degrees Celsius, and high temperature insulation, which is 325 degrees Celsius and above. Okay, so you see that this is the basic calculation which we have done. We are not going to discuss much in detail over here. Okay, but you see that this particular calculation is done for 1 inch, 2 inch and 3 inch insulation for a same diameter pipe with carrying the same temperature. And you see that the economic insulation, you see that the total cost or insulation and net present value of heat loss is shown over here. You see that lesser value is obtained for 2 inch of insulation. So optimum value of savings of energy is not for if the insulation thickness it goes on increasing, the price goes on decreasing. It is not like that, but you have to calculate the optimum insulation required, and which will give me a better net present value of the change. Okay, so this particular calculation is available on the slide. You can go through it, no problem with that. Okay, before we end up with the insulation part, I would like to tell you the difference between the critical thickness and economic insulation. So optimum insulation is the insulation at which the capital expenditure is lesser. And what is the how we can calculate the insulation of the material? Here we have the formula for conduction, which is the delta T upon the RTH, whereas RTH is the resistance, thermal resistance offered by the material, and thermal resistance offered by insulation is given by 1 upon HA, which is the convective heat transfer coefficient from inner side, plus 1 upon H outside, which is the convective heat transfer coefficient offered by outside area, and plus L by Ka. So L by K is length of the thickness of the insulation upon K, thermal conductivity and area of the conductor. In case of cylindrical system, it becomes 1 upon 2 pi KL ln of R2 by R1, where R2 is the outer radius of the insulation and R1 is the inner radius of the insulation. So here we can do the optimum thickness which can be required. So how to calculate, by the way, economic thickness of insulation? There is a method to calculate the economic thickness of insulation. First, you determine all the parameters. That means what is the pipe temperature, diameter, length, surface area, what is the temperature to be maintained, insulation material, so its conductivity from handbook, everything you select. Then you calculate the heat loss from bare wire or bare tube without insulation. You will get some value. Then you calculate the insulation of optimum value. So just increase the insulation, create an Excel sheet, put your insulation value in the multiples of 1, 2, 3, like that. So you see that you will get a graph representing how the economic feasibility is taking place, and then you will end up with one optimum value at which the insulation will become economical, and that should be your, and at that point you can calculate the net present value, the life of the insulation can be put up. So see, now I would like to introduce one term which is called as annualized life cycle cost. Okay, so annualized life cycle cost, what is the meaning of this? So you have the insulation has some thickness and it will have some life. Let us say the life of that insulation is 5 years and your simple payback period comes for 3 years. Then your annualized life cycle cost will not be calculated with 3 years time, but it will be calculated for 5 years time. And then after 5 years, it will become salvage. Okay, salvage means it will be of no use. It can be, it is a scrap, right? So that is the meaning of annualized life cycle. So life cycle cost and annualized life cycle cost you have to calculate for a given material, and then you can say that this insulation is better for my application. Okay, having said this, let us summarize what we have done up till now. And we started with furnaces. We have done the classification of furnace. Then we talked about the general fuel economy in furnaces. and discussed about how the excess air or the location of wall or conductive heat loss hampers the economy. Then okay, then we talked about how we can minimize the heat loss from the furnaces, right? So all these things we discussed. There is a direct and indirect method of efficiency calculation. Then uh, how to have the optimum capacity utilization or waste heat recovery from the flue gas. We talked about some ceramic coatings or ceramic fibers, refractory coatings. Okay, then operating the furnace at desired temperature. Then we talked about the uh, insulation, types of insulation. What are the advantages of using an insulation? So these all with things we have discussed. We have talked about differences between critical thickness of insulation and economic thickness of insulation. We talked about the fishbone diagram of furnace. Then we talked about the uh, overall life cycle cost and annualized life cycle cost of the system or the process. Okay, so any questions up till now?